You know, even I can get annoyed, so. All right, there we go. So let's finally fuse those nuclei together that we've been trying to fuse here, so to speak. And so last time we were talking about this idea of, where do we begin? Let's see. So we had written down an expression for the height of the Coulomb barrier at the point of kind of classical closest approach of the two particles. So there's the energy coming in there, and there's the Coulomb barrier. And so UC over E refers to, okay, here is the height of the Coulomb barrier at the classical turning point that the incoming particle reaches. Really, again, we're in the what word am I looking for? The center of mass frame. So how close do the two particles get to one another? How big is the Coulomb barrier at that point? And so we said that it has to get to within about a de Broglie wavelength, blah, blah, blah. So as the energy decreases, that gets smaller and smaller. And so it's reaching a barrier that is higher and higher, which in and of itself would make you think, oh, it's harder to do. But on the other hand, the closer they get together, the smaller is the distance that it needs to tunnel through. This is the distance that it needs to cross through with magic quantum mechanics goodness in order to feel the strong force attraction. And so with some waving chicken feet and so forth, we decided that this ratio of the height of the Coulomb barrier to the incoming energy was important, and that was equal to, when we plugged everything in, let's see, did we write that it was mu to the 1/2 Z1 Z2 E squared over 2 to the 3/2 pi epsilon naught H e to the minus 1/2? I think we wrote that last time. You're looking at me like I have no idea. What?
Maybe not.
Maybe not. Okay. So I think we did say this, that okay. So let's do this. That UC would be Z1 Z2 E squared times the reduced mass times V over 4 pi epsilon naught H. I think we did say this. Yeah, we did say that. Because we were saying that our classical should be on the order of the de Broglie wavelength, H over the momentum. But on the other hand, because the momentum was whatever it is, so E squared over 2 mu, M would be the energy, and so that would say that P is square root of 2 UME, so this would be H over square root of 2 mu ME here, mu M times E. And so the Coulomb barrier is product of the charges Z1E times Z2E over 4 pi epsilon naught R classical, because we're saying they want them to come within, well, the height of the Coulomb barrier when they are within the classical turning point of one another would be Z1E, Z2E, product of charges over 4 pi epsilon naught R classical, because that's the expression for the Coulomb potential energy in general in terms of the charges and the radius of separation. Then we would put in what our classical is here, Right, but this is, just move this off the cuff here. Kind of in the middle here. Right, but this is, if we put it, that's what over here. It would be what I just wrote, but it also is H over mu V. Because P is MV, P is mu sub MV. So I put in H over mu sub MV in for our classical. So that puts mu MV on the top and H on the bottom there. So that's where this is coming from. Okay? So then, we say then that UC over E is therefore UC over, if we do things in terms of the velocity, 1/2 mu sub mv squared. So that's going to be 2z1 z2 e squared over 2 pi, over, whoops, what am I doing here? Oh, okay. Right, the 2 just comes up there, and then, what am I doing? Oh, okay, so now I am going to put in the expression, where am I? 2z1 z2 e squared over 4 pi epsilon naught times h v. Right, so now I'm just plugging this in. Right, this I'm just dividing through by 1/2 uv squared. So I put 2 up on top and a mu on the bottom would cancel this mu there, and then you still, and then you. It looks right. It looks right. Okay. Yeah. All right. Thank you. Equals z1 z2 e squared over 2 pi epsilon naught h. Now we substitute that v is 2e over the square root of u sub m to the 1/2. Since e is 1/2 mu v squared, then v is square root of 2e over mu sub m. So this becomes mu sub m to the 1/2 times, because we got a 1 over mu to the 1/2 here, so that can come up top. Mu sub m to the 1/2, z1, z2, e squared over 2 times 2 to the 1/2 is 2 to the 3/2 pi epsilon naught times h, and then finally e to the minus 1/2 power, because we've got 1 over e to the 1/2 is e energy to the minus 1/2 power. And by the way, I should have mentioned that the reason we care about this is because last time we had said that the probability of barrier penetration turns out to be proportional to e to the minus 2 pi squared times uc divided by e. So that's why we care about that ratio of uc over e, because e to the minus 2 pi squared times that is the probability of barrier penetration. And so if we plug our expression for what UC over E is into the probability of barrier penetration, we say that E to the, let me write it again, probability of barrier penetration, the chance that we're going to tunnel, looks like E to the minus 2 pi squared UC over E. Well, that is E to the minus B, E to the minus 1/2, where we've just put all these other factors into B. In other words, we just say B, just to simplify the writing, is equal to, by definition, pi times mu sub m to the 1/2 C1 C2 E squared over 2 to the 1/2 epsilon naught H, which is just a bunch of constants. So we fold them all together and call that constant B. And here we note that B depends on the electric charges of the two nuclei. Whose golden light is to fuse with one another. Increasing the charges decreases the reaction cross-section. It makes them less likely to fuse with one another. Because the barrier penetration probability there comes into determining how likely they are to fuse with one another. And so we've got E to the minus B, capital energy, capital E to the minus 1/2. So the bigger B is, the smaller is the barrier penetration probability, because it's E to the minus B, capital E to the minus 1/2. Why does it make sense that if you increase the charges, they're less likely to fuse with one another? Yes?
They're more repellent?
Yeah, they're more repellent of one another. They're repelling one another more strongly, and so it's harder to make them fuse. Yep. All right. Okay. What questions do you have at this point?
I'm trying to understand what does it mean to increase the charge.
In other words, put more protons in. This is saying it's harder to fuse to, all else being equal, right? If the only difference is the electric charge, just on that basis alone, it would be harder to fuse, say, 2 helium nuclei together than 2 protons together, because the protons, there's 2 protons in each helium nucleus, and so they feel a strong repulsion force for one another. Yep. Okay. And so, we're almost at our payoff here after all of this prestidigitation. So as a reminder, and we should have started with this, we were saying that the reaction cross-section was some, we assume, slowly varying function of energy that captures the gory details of nuclear physics. Remember that from last time. times the effective cross-sectional area times the probability of barrier penetration, which is what we were just talking about here. And again, from last time, we said that the effective cross-sectional area was expected to be pi times the de Broglie wavelength squared, which would be pi times h over p squared. And we had argued that this then was equal to pi h squared over 2 mu m e, putting the fact that p squared is equal to 2 mu m e in there, so that this looks like 1 over e. And we just argued that the probability of barrier penetration is e to the minus some constant, energy to the minus 1/2. So base of the natural logarithms to the power of a constant b times the energy that they're coming in towards one another with in the center of mass frame times e to the minus 1/2. And so if we put this all together then, we are saying that the interaction cross-section for fusing is that slowly varying function of energy times e to the minus b energy to the minus 1/2 divided by e. So we can fold everything else into the S of e, any other extra constants lying around like the pi h squared over the 2 mu m, that could just get folded into S of e term. Questions, comments, observations? So that's the interaction cross-section as a function of energy. And so, Rix, which remember is supposed to be the rate at which incident nuclei I are fusing with target nuclei X per second per kilogram. Sorry, per second per cubic meter, right? So this was, I'll write that down again as a reminder. That's the number of reactions between nuclear species I and X per cubic meter per second. That's how many of those fusions of those nuclei are going off per cubic meter per second. This was NINX, the number of I nuclei per cubic meter times the number of X nuclei per cubic meter times this sigma V IX, funny notation that we used. But that funny notation meant this integral right here, integral from 0 to infinity of sigma of E v of E P of E dE and we, from today and Wednesday, have all of the ingredients to put into that integral now. So we will do that. This is NINX, integral from 0 to infinity, integrate over all energies of S of E times E to the minus B, E big E to the minus 1/2 over E. So all of this stuff, this term is the fusion cross-section as a function of energy. That's the sigma of E term. Meanwhile, V as a function of energy, that just means how fast they're moving relative to one another in the CM frame for a given energy E. So see if you can remind me of that, see if you're following along here. How is the energy related to the reduced mass and the speed that they're moving relative to one another in the center of mass spectrum? How fast they're moving relative to one another. How is E related to that? Hint, it's their kinetic energy in the center of mass frame. So how are speed and kinetic energy related to one another? If we're not talking about relativity, if we're assuming Newtonian physics, what's the formula for kinetic energy in terms of mass and speed? That's what I'm asking. 1/2 mv squared, except it's the reduced mass. So it's 1/2 mu v squared, yes. The cal says 1/2 mu v squared here, right? 1/2 mu sub m v squared. And so that says that v is just the square root of 2e over mu. Mu sub m, it's the we're using mu sub m. I could just say mu, but we're both using mu sub m, so I've been using that. The reduced mass mu sub m of the two particles. So we put in, for the V of E, we put in 2e over mu sub m to the 1/2. So that's why that term appears. That's just how fast they're moving relative to one another. And then in the homework, you show that, so this is, I should be explicit here, so this is V of E, that's the V of E term. In the homework, you show, how do you show it? Joyfully, we joyfully show in the homework that P of E dE is in fact 2 over pi to the 1/2 times quantity kt to the 3/2 power e to the power of 1/2 e to the minus capital E energy over kt dE. So this is P of E, joyful homework. That is the integral that one does to calculate the fusion rate for nuclei of species I and species X. So, if you know the masses of the nuclei and you know how many protons are in each one, you've got all the ingredients to plug into this formula. The one tricky part is the S as a function of E, and that's a job for the nuclear physicists to come up with. And so, sadly, we're not actually going to literally do the integral, but we want to understand something important about it, namely the Gamow peak. So let me get the projector going here. And meanwhile, I will say that this piece right here, the e to the minus b e to the 1/2 times e to the minus e over kt exhibits a peak called the Gamow peak. Oh, actually, no, okay. Forget, don't circle all that. I meant to write another line here. We want to simplify all of this, what we've written here. I forgot to write the next line. This is just one of those days. Don't you hate it when you forget to write the next line? You know, I do. All right. So, because we got a lot of junk there, so we can simplify, right? There's like e to the 1/2 and e to the 1/2 appearing again. So, Rix, when you simplify, is we can pull out 2 over kt to the 3/2 power NINX over reduced mass times pi quantity to the 1/2 power, and now it'll be the integral from 0 to infinity of S of E, going to nuclear physics, but we think it doesn't depend strongly on energy, e to the power of minus b, energy to the minus 1/2, e to the minus e over kt dE. So this gets the box. This is what we were finally after. Because notice that e to the 1/2 times e to the 1/2 is e divided by e. It just cancels out. That e goes away. And then we can pull the other junk outside, and so we're left with the integral being S of E, doesn't change very much with energy, times the factor e to the minus b, e to the 1/2 minus 1/2, e to the minus e over kt. So now we want to talk about the Gamow peak. So, this beast right here, e to the power of minus b, energy to the minus 1/2, times e to the minus energy over kt, inside the integral, in other words, in the integrand, exhibits a peak called the Gamow peak, after George Gamow. At energy E0 equals BKT over 2 to the 2/3 power as you should show in the homework. So you will show that the maximum of this product occurs at that particular energy. How will you show it in the homework? You will show it joyfully, of course, yes. You will joyfully show that. Bring up the figure from your text that shows what we're talking about here. So here it is. So this is a plot for, I believe it's the proton-proton chain, if I'm not mistaken. So it's, no, I mean, I think it's the plot for 2 protons fusing, if I recall correctly. And so this is the energy in kilo electron volts, kinetic energy of them coming in keV. And here is the plot of e to the minus e over kt. In keV at the temperature of the sun's core. And here is the plot of e to the minus b, e to the minus 1/2 divided by 1,000. So in other words, you can multiply it by 1,000 at the temperature of the sun's core, or 2 protons fusing with one another. And you multiply the 2 dashed functions together and multiply that by 1,000,000 to make it show up. And you get this solid function right here. And the Gamow peak is literally the energy at which that product is a maximum. So it's just where that's a maximum. That's E naught when you plug in the temperature of the sun's core and 2 protons fusing together with one another. So how do we interpret this, right? So remember, this is in the integral that we're performing here. It's not, we're integrating over energy. So what we're talking about is the thing that we're integrating over energy. S of B is nearly a constant, so to this approximation, you could actually evaluate that and pull it out of the integral. And so we're making the integral of e to the, this term times this term, which I would say e to the minus b, e to the, all that. So this piece right here, that, say it again, e to the minus b, e to the minus 1/2, that is the barrier penetration probability. And the e to the minus capital E over kt is from the Maxwell-Boltzmann distribution. So what does the Gamow peak mean? Well, first of all, the total reaction rate between 2 protons in the sun's core at the center, where the temperature is like 16 million Kelvin, you would evaluate this integral, evaluating over all energies from 0 up to infinity. Now it would break down when you got to energies where the particle was relativistic, but at the sun's core temperature with 2 protons, they're well in the non-relativistic regime. And so here's this function of energy, and then some function of energy, and I'm going to integrate that. What is an integral? Geometrically speaking, if I integrate that, the total what is the reaction rate? The area under the curve, right? Yeah. So, area under curve, total area under curve, equals the reaction rate. If this is some energy E sub 1 and that's some energy E sub 2, what does the area under the curve between E1 and E2 represent? So if I did the integral from E1 to E2 of stuff, all that junk, dE, that should be E to blah, 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 times all that stuff, the whole thing. What does that area represent?
Delta stuff,
What's that?
the difference between the energies.
No, so I'm saying I integrate all this stuff. I do this integral, I do the whole integral between E1 and E2. What does that represent in particular? If I integrate from 0 to infinity, that's the total reaction rate. If I integrate from just E1 to E2, that is the
reaction rate for particles within those energies.
That's right, that's right. This will be the reaction rate for particles in the energy range between E1 and E2. For particles with energies between E1 and E2. The total area is the total reaction rate. If I just take a slice of it, that's the reaction rate due to particles whose energies are in that slice. So if I took a bunch of equal-sized slices, there's a slice, there's a slice, there's a slice, there's a slice. Which one of those equal ranges in energy is associated with the largest percentage of the reactions that are happening? Clearly, the ones where that function that we're integrating is tallest. Why? What do we call the place where that function is tallest? The energy where that function is at its tallest. We call that we call it the gamma peak. The gamma peak, yes. Yes. In other words, the interpretation of the gamma peak is that the energies near the gamma peak are where most of the reactions are happening, so to speak. That's the energies where most fusions are happening at. Interpretation. Energies near E naught are where the most fusions are occurring. That's how we interpret the gamma peak. That's the energy, that's the energy for two protons, again, relative energy in their center of mass frame, that is most likely to produce fusion. So in the solar condition about what is that energy. What is E naught? Give me an estimate of E naught in keV. Yeah, 6 keV, around 6 keV. So protons coming in with about 6 keV of energy actually are associated with the largest number of reactions. But that doesn't mean that 6 keV is the best energy for two protons to fuse at, right? Because there's a combination of things here. The barrier penetration probability is telling us how likely two protons are to fuse if they have that energy. And that's definitely getting bigger and bigger as the energy increases. If I have protons coming in with 10 keV, they're much more likely to fuse than two protons coming into one another with 6 keV. If they have 10 MeV, they're vastly more likely to fuse than if they have only 6 keV. The faster they're moving, the more energy they have, the more likely a pair of protons is to fuse with one another. So why is it that even though two protons with 10 keV of energy are much more likely to fuse with one another than two protons with 6 keV of energy, and two protons with an MeV of relative energy are vastly more likely to fuse than two protons with 6 keV of energy, why are most of the fusions around 6 keV of energy? Why does that happen? Yes?
Is it just that it's more common for protons to be around 6e?
Exactly. There's hardly any protons with much larger energies than that. There's just hardly any of them there. That's why it's a competition between two terms. The Maxwell-Boltzmann distribution is tailing off here. The peak is way over there somewhere. The Maxwell-Boltzmann distribution is tailing off. Fewer and fewer protons, pairs of protons have this much energy, have a given amount of energy as you increase the energy. There's less and less of them. At the same time, the higher the energy they have, the more any given pair would be likely to fuse. And so the gamma peak is the compromise where there's still enough of them around, so to speak, to get a significant number of fusions. So it's a competition between two terms. Fewer and fewer protons have a lot of energy, but the more energy protons do have, the more likely any pair is to fuse with one another. So the gamma peak is where you kind of split the difference. It's sort of similar to when we talked about Goldilocks and the 3 stars, right? In other words, the higher the temperature, the greater the fraction of neutral atoms there will be with their electrons in n equals 2 ready to absorb Balmer series photons. But at the same time, the higher the temperature, the fewer neutral atoms there are to begin with. And around a little bit less than 10,000 Kelvin is where you get the kind of sweet spot where you've got a high enough temperature to produce, to still have a reasonably large number of neutral atoms, and at the same time, have some of them being kicked up into n equals 2. There's two competing factors, and the 10,000 Kelvin is around the sweet spot. Higher temperature puts more energy in neutral atoms more electrons in neutral atoms into n equals 2. At the same time, it's eliminating neutral atoms. Over here, higher temperature is making pairs of protons more and more likely to fuse with one another, but because of the Maxwell-Boltzmann distribution, there are fewer and fewer such pairs of protons around to have the potential to fuse with one another. And the gamma peak is where the product of those two competing terms, one that decreases with energy in terms of the number of protons around at those energies, another that increases of energy that says, yeah, but if you are around, you're really wanting to fuse, it's the compromise, so to speak. Does that make sense? That's the idea here. And 6 keV is actually a very low fusion probability. And so most of the protons that are fusing in the sun have classically what would be not nearly enough energy to fuse, but tunneling works its magic and a tiny fraction of them do fuse because there's enough of them around that the tiny fraction of them that do fuse keeps the sun powered, essentially. Okay? Ta-da! Time for a break at this point. I'm realizing that I hadn't shown the entire graph in the video for the people at home. So here it is now, people at home, please enjoy. I'm sure that you got out your notes and got out the slides I passed around and you were looking at them as I was talking about all this. A couple more things here, then it's finally time to move out of chapter 10 into chapter 12 about the interstellar medium, which a very large fraction of the pretty pictures you see are pictures of the interstellar medium. But first, let's enjoy a little bit more of fun with fusion here. So, usually we write epsilon, the energy generation rate per kilogram, in terms of the mass density rho. In terms of the mass density rho, instead of the concentrations n, instead of concentration n, concentration, again, is just another name for number density. And Ni would be rho capital X sub I over M sub I, where Xi is the mass fraction of species I, the fraction of the total mass that is due to species I. So if it were 0.5, half the mass of the particles would be species I particles, etc. And Mi is the mass of the nucleus of species I. You can include the electrons with it too if you wanted, because they're so tiny compared to the nucleus. So actually you might, I will just say an atom of species I, because everything normally would include its electrons too, even though they're only like 1/2000. Because deep in the sun, there ain't no intact atoms. So, why would this be true? Well, because the density times the fraction of the mass that's due to species I will be how many kilograms are of species I per cubic meter. Right? If there's 1,000 kilograms per cubic meter and 0.3 of those are species I, then there's 0.3 times 1,000 is 300 kilograms per cubic meter of species I. And if you divide how many kilograms there are in every cubic meter by how many kilograms there are for every atom of species I, that'll be how many atoms of species I are in every cubic meter. Just like if we had a bunch of people that all had the same mass, and I told you their total mass in this room, if you divide by the mass of any one of them, that's how many of the people of that type there are in this room. Here we're just applying that to the atoms. So number of atoms of species I per cubic meter will be the number of kilograms of species I per cubic meter divided by the number of kilograms per atom of species I. Does that make sense? What questions do you have? What we're doing with that? So Ni and x will then be proportional to rho xi, proportional to, I'm not going to bother with that division by the masses, rho xi times rho xx. So that'll be rho squared times x of I times x of x, big X of I times big X of x. Do you remember, what do we call the mass fraction of hydrogen typically? What capital letter do we use for that? Astronomer periodic table. What do astronomers call the mass fraction of hydrogen? That's capital X. What do they call helium? That's Y. What do they call everything else? Yeah. Z, right? So to astronomers, there's three elements, X, Y, and Z, so to speak. Here we're being more specific. Here we would, for saying generically, this could be like, for example, capital X of helium-4, capital X of praseodymium or whatever. That's what the Xi and XX are referring to there, as opposed to just more generically helium, hydrogen, everything else. But if we do just say X, it means hydrogen. If we just say Y, it means helium. So Rix is, again, number of reactions per cubic meter per second. But epsilon depends on, it depends on, it's proportional to number of reactions per kilogram per second. We multiply that by how much energy comes about of each reaction to get epsilon. So reactions per kilogram per second times energy per reaction would give us epsilon. So epsilon depends on the number of reactions per kilogram per second. So we divide Rix by rho to get what we're looking for here. Divide Rix by rho. I.e. we're multiplying by rho is kilograms per cubic meter, so if we multiply by, like we were doing before, cubic meters per kilogram, that would turn us into reactions per kilogram per second. So epsilon is going to be proportional to, we're dividing by rho to get the epsilon from Rix. And I'll say here Rix is proportional to Nix, which is rho squared, which is, so then proportional to rho squared XIXX, divide by rho to get what epsilon depends on. So that kills one factor of rho in that expression. So we get this epsilon should be proportional to just one power of the density times the product of the mass fractions. I've been known to ask on an exam why epsilon should be proportional to rho xi(xx). Not that you'd have to go through the full derivation we went through of everything, but be able to explain why this should be true, that it should be proportional to the product of ni and x. So let's review. Why should Rix be proportional to ni times nx? In other words, this is saying if I were to double the number of x nuclei per cubic meter, I get twice as many nuclear reactions of the type we're talking about per cubic meter. Intuitively, why should doubling the number of target nuclei per cubic meter double the reaction rate? If you double the number of targets, what happens?
There's more targets.
More targets to hit. Yeah.
Cross-sectional.
Yeah, twice as many targets to hit, so that'll double the reaction rate. Similarly, if I double Ni, twice as many incoming would also double the reaction rate. From X's perspective, I is the target. Which one you call the target and which one you call the incident is completely arbitrary. So intuitively, you get Ni and X because increasing either one of these will increase the reaction rate in proportion. More targets or more incident is going to, in proportion, increase the reaction rate. And then, since they're both proportional to rho times xi, that's why rho squared xi(xx) should be, the reaction rate per cubic meter should be proportional to rho squared xi(xx). And epsilon is defined per kilogram, so we have to divide by rho, so you get rho xi(xx). So you should be able to trace through that logic without having to go through that long derivation of what Rix actually is in terms of the fancy integral and all that. That's the, be able to, on an exam, be able to explain it to that level, which of course invites the question, what questions do you have? So one thing that we have not accounted for, and we're not going to do it in any detail, but just know about it. A factor we haven't accounted for that the pros need to know about is electron screening. And that reflects the fact that in the sun's core, everything's ionized. It's so hot, everything's ionized. You got nuclei approaching one another, trying to fuse with one another. They're positively charged, they're repelling, but there's also electrons around in between them, and that partially shields their own positive charges from one another, making fusion a bit easier to happen because the negative electrons partially screen the positive charges on the protons of the nuclei that are approaching one another, which reflects the fact that electrons partially shield the positively charged nuclei from one another. Reflects the fact that free, unbound electrons partially shield nuclei from one another. Shield the positively charged nuclei from one another. Reducing their mutual repulsion and thus increasing the reaction rate, enhancing the reaction rate. So when the pros go about their business, if we look at that reaction rate integral, epsilon for the combined PP chain, all three branches, is calculated to be this monster. Epsilon PP is 0.241 rho x squared F sub PP, psi sub PP, C sub PP, big C sub PP, T sub 6 to the minus 2/3 e to the power of minus 33.80 T sub 6 to the minus 1/3 watts per kilogram. T sub 6 means the temperature over 1,000,000 Kelvin. So in other words, if the temperature is 16 million Kelvin, T sub 6 would be 16, for example. So it's just scaling the temperature, just expressing the temperature in terms of millions of Kelvin. So in general, T sub n is T over 10 to the nth power Kelvin. Welcome. You can come up closer if you want, it's fine. You seem to like to give it up. You're welcome here. We're a friendly astrophysics class. FPP is about 1 for the proton-proton chain, it turns out. And psi PP, which is also about 1, is a correction accounting for the fact that there's 3 branches. So in other words, this is saying how the proton-proton chain reaction rate depends on temperature. And CPP involves some higher order corrections. Near T6 equals 15. What temperature is that? If T6 is 15, the temperature itself is 15, 15, make it simpler than that. T over 10 to the 6. What's 10 to the 6? What's another name for 10 to the 6? A million, right? So T6 being 15 means 15 million Kelvin. That's all it means, right? So don't be confused by the notation, in other words. Why would we choose 15 million Kelvin? Because that's around the sun's central core temperature. It's a little higher than that, but that's about the sun's central core temperature. So that's where we're interested in if we're talking about the sun. this approximates to epsilon pp is about 1.08 times 10 to the minus 12th power watts per cubic meter, watts meter cubed, I should say, per kilogram times rho x squared, psi pp, which is about 1, fpp, which is about 1. Here is the kicker right here, t sub 6 to the 4th power. That's really the piece to pay attention to. T6 to the 4th power. So, a couple things. Got rho x squared right there. Got rho x squared right there. Why is it rho times x squared? What is x? It's the mass fraction of, that would be x up cute little x. This is a capital X with no subscript. So it's the generic capital X. A capital X with no subscript, astronomers say, why that must be mass fraction of hydrogen. Yes, it's hydrogen, right? So it depends on the density times the hydrogen mass fraction squared. Why is it the hydrogen mass fraction squared? Generically, it was rho x sub I, x sub little x, when species I and x are fusing. For the proton chain, while there's all these branches, and that's why there's the correction factor in there, the first step, and remember all the steps happen at the same rate in equilibrium, the first step involves what incident species and what target species are involved in the first step of the proton-proton chain, yes?
I think 2 hydrogens used to make deuterium.
2 hydrogens used to make deuterium. So species I is good old hydrogen, and species X is good old hydrogen. So XX is just capital X, capital X. It's both hydrogen. So it's rho x squared, because it's 2 hydrogens that are starting this sequence off. So that's one thing, right? It's, they're both hydrogen. Xi equals x sub x equals x. It's hydrogen. It's hydrogen, so that's why it's rho x squared. And it's T6 to the 4th power. So, if you change the temperature a little, the reaction rate increases a lot. It goes like a temperature to the 4th power. Nuclear reaction rates are very sensitive to temperature. The temperature to the 4th power is very sensitive. And this is playing into, remember, and I'm going to show it for the CNO cycle soon, and it's similar for other species. Remember, let's see, if I've got 2 stars, and one of them is 1 solar mass, and the other is 1.1 solar masses, which one has more fuel to burn, so to speak? The 1 solar mass or the 1.1 solar mass? The 1.1 solar mass star has more fuel to burn. If they burn the fuel at the same rate, which one would live longer as a result of that?
1 solar mass.
If they burn the fuel at the same rate, they don't, but if they burn fuel at the same rate, which one will last longer? If a Prius and a Hummer burned gas at the same rate, which one would go further with its bigger gas tank? The bigger gas tank, the Hummer would go further, right? A 1.1 solar mass star has a bigger gas tank than a 1 solar mass star. So if they burn fuel at the same rate, which one would last longer? The 1.1 solar mass star would last longer. But which one actually lives longer? The 1 solar mass star does. Why? Because they both have to, the reactions in their core are what are providing the pressure to support their overlying layers, okay? So the 1.1 solar mass star has more weight to support, so to speak. The outer layers above the core are literally heavier, okay? And so the way the core does that, it's a play between density and temperature, but the way it works out is the core of the 1.1 solar mass star has to be a little bit hotter in order to support that extra weight. It's got to be just a little bit hotter than the core of the sun to support that extra weight. Make sense? 1.1 solar mass star's core needs to be a bit hotter because, P is rho kt over mu mh, density times temperature times K over the mean molecular weight. Well, K over the mean molecular weight is the same for both of them, and rho is different. It turns out it's a little smaller for the 1.1 solar mass star, so there's two factors there, but it turns out the biggest difference, the biggest factor, in the end, the temperature of the 1.1 solar mass star's core is a bit higher than the sun's temperature. A little higher. But the reaction rate for the proton-proton chain goes like temperature to the 4th power. So a little extra temperature needed to support that weight means you have to have much faster reactions in proportion. The increase in the nuclear reaction rate is more than the increase in the temperature. This is fundamentally why more massive stars live shorter lives, because their cores have to be hotter to support the extra weight. The fact that nuclear reactions are very temperature sensitive means there's an outsized increase in reaction rate associated with that rise in temperature needed to support the extra mass. And that's why they got more fuel, but they more than make up for it by burning it faster, by burning it at a much higher rate. It's roughly mass to the 3.5 power is the rate at which they're burning the fuel. 10 times the mass is roughly 3,000 times the fuel burning rate. The temperature is nowhere near 3,000 times larger, but the reaction rates are so sensitive to temperature that just a little extra temperature requires a disproportionate increase in the reaction rate. You need a little extra temperature to support an extra mass, but that much out of proportion increases the nuclear reaction rate required to bring about that extra temperature. That's the crucial key point there. Kaboom! Right, that's the deal there. Should I write all that out? You got that down?
Got that on the video.
It's on the video, that's certainly true. Do you want me to write it out more specifically, or you good, or should put you on the spot here? Anybody want me to write it out, or?
Maybe you could get a little portion of it.
Okay, so let's make the argument here, okay? So, why do more massive stars live shorter lives? Right, this is our question. Why do more massive stars live shorter lives? Even though they've got more fuel. Right? At least when they're on the main sequence, that's hydrogen to burn. Well, the core pressure needs to support the weight of the layers of the layers above the core. this is accomplished, again, it's a little more complicated than this. It's not immediately obvious that this does it because P is density KT over mu mH, mass of a hydrogen. So both density and temperature play in the pressure. And so there's both of them there. So is it, what predominates here? Well, you have to actually do the calculations, right? Make your stellar model or whatever to figure that out. This is accomplished by the core temperature being higher in high mass stars. In higher mass stars. A more massive star has a hotter core. It needs it to have the pressure needed to support the weight of the layers above it. But the nuclear reaction rate is very sensitive to temperature. So, for example, we saw that for the pure proton-proton chain, for a star like the Sun, the nuclear reaction rate goes like the temperature to the fourth power. And that says a little extra T implies a lot of extra nuclear reaction energy generation. That's kind of the gist is you need to be a little hotter, but that means that really steps up the nuclear reaction rate out of proportion. This is why higher mass stars more than make up for their extra fuel by burning that fuel at a higher rate. Burning it at a faster rate. It's that whole story. And in fact, remember that roughly speaking, in the middle of the main sequence, it works out that the star's luminosity over the sun's luminosity is approximately its mass over the sun's mass to the 3.5 power. So doubling the mass way more than doubles the luminosity, way more than doubles the rate at which it's burning the fuel. The whole business. You buying what I'm selling? That's the deal there. It's one of the most fundamental things for an astronomer to know. But you know what? I'll bet you could go pick random astronomy grad students and some of them wouldn't be able to answer that. They wouldn't know that argument, I'm guessing. So, you will. You know the argument. You're awesome. You're welcome. Okay? All right? But wait, there's more. So the proton-proton chain, temperature to the fourth power. Let's look at the CNO cycle. So remember that, that's the one where it's starts with carbon 12, and you make various isotopes of nitrogen and oxygen until you get the carbon 12 back and helium-4 nucleus. So for the CNO cycle, near T to the 6, T sub 6 equals 15. The power law approximation is epsilon CNO is approximately 8.24 times 10 to the minus 31st power watts per meter cubed per kilogram to the minus 2 times rho x CNO. So x CNO is the total mass fraction of carbon, nitrogen, and oxygen, because all three are involved as intermediates. T sub 6 to the power of 19.9. T to the almost 20th power. Now that's a dependence on temperature. Super strong dependence on temperature. Wow! Look how strongly that depends on the temperature. Okay? So, think of increasing the mass along the main sequence. The sun is powered by mostly the proton-proton chain. There's some CNO, but it's mostly the proton-proton chain. If you go to stars of higher mass, what happens to the core temperature as you go to higher mass? Higher temperature. So does the proton-proton reaction rate increase as the temperature increases? Yes, it does. Does the CNO cycle reaction rate increase? Yes, it does. Which one increases faster? CNO, because it's T to the 19.9 instead of just T to the 4. So as a result, as we go up the main sequence towards higher masses, the CNO cycle takes over because it's much more sensitive to temperature than the proton-proton chain is. And it turns out that really the sun is about near the upper limit of how massive a star will be and still be powered mostly by the proton-proton chain. 2 solar mass star, it's CNO. 3 solar mass star, it's CNO. I think I got this out of the book. In my notes it says about 1.2 solar masses is the cutoff. Over 1.2 solar masses and above, it's CNO. And so I always just kind of believe that. And then James Durley did a senior project with me a couple years ago where he used MESA to study the modules for experiments in stellar astrophysics. It was professional stellar evolution code. And we were looking at CNO cycle versus proton-proton chain in stars, and we were trying to figure out, well, where does it switch over in terms of mass? And we learned, oh, it's way more complicated than that. Actually, any given star kind of close to the sun's mass will, when it's young, be using the proton-proton chain, but as it ages, it eventually switches to the CNO cycle. And the reason for that is that as the sun fuses hydrogen in its core, what's happening to the amount of hydrogen versus the amount of helium? As the sun's fusing hydrogen and helium, so starting out, about what fraction of the sun's core is hydrogen and what fraction of the sun's core is helium?
Hydrogen is about 70.
Yeah, hydrogen's like 71, something like that. And helium's like 27, 28, I forget what it is. But I wrote it down not long ago about what the mass fractions were. But as you know, it's roughly 3/4 hydrogen, 1/4 helium is what stars typically start out as, roughly. Well, now, because the sun has been fusing hydrogen and helium for the last 4.5 billion years, the sun's core now by mass is about 65% helium and 35% hydrogen. It's actually, there's more helium by mass in the sun's core than hydrogen now, if you go to the center of it. And that is reducing the number of particles in the sun's core, because for a given amount of mass, a helium nucleus has 4 times the mass of a hydrogen nucleus, so the number of particles in the sun's core is diminishing. Put another way, the mean molecular weight is increasing. The average mass per particle is increasing as more and more of the particles become helium nuclei as opposed to hydrogen nuclei. So I think I'll write this out too. It's actually a good thing to understand. So as fusion progresses, in a main sequence star, core. What's it mean for it to be on the main sequence? On the HR diagram, it's on that diagonal S, right? But what's happening inside the star that makes it the main sequence star? Fusing hydrogen and helium, and where is it doing it? In its core, right? So hydrogen fusing into helium is increasing Y at the expense of H. What's Y again? The helium mass fraction versus the hydrogen mass fraction, right? So more and more helium as opposed to hydrogen. Today, the solar core has Y as something like 0.65. There's actually more mass in helium in the sun's core today than there is in hydrogen. So the mean molecular weight, mu, is increasing. Remember, mu is the average mass per particle in terms of the mass of a hydrogen atom. And the sheer number of nuclei is decreasing. Actually, I'll get 4H becomes helium. To emphasize, 4 hydrogens are making a single helium, so the number of nuclei is decreasing. So if mu is increasing, and that was the only thing that was happening, what would be happening to the pressure inside the core? It would be decreasing. This would on its own make P decrease, but that can't happen. It's got to still support the outer layers. So what happens? The temperature has to increase to compensate. But that can't happen. core still needs to support the weight above it. So T is slowly increasing as the sun ages. T in the core is slowly increasing as the sun ages. So what do you think that's doing to the nuclear reaction rate inside your core? It's increasing it because it's super dependent on temperature. Again, there's multiple factors. Okay, there's fewer protons around too. That in and of itself would lower the reaction rate, but the temperature dependence is more important than that. And so the nuclear reaction rate is slowly increasing. And that says sun is slowly brightening. The sun is getting more luminous with time. And models indicate that the sun on the ZAMs was only about 60% of its current luminosity. It would be noticeably dimmer when it was on the ZAMs. Now you have to remind me, what does ZAMs stand for? ZAMs, I hate yams, which is true, but that's not anything to do with yams. They're disgusting. Disgusting. Ugh. You're wrong.
You're wrong.
No, you're wrong. You're wrong.
Fine.
So would you rather have sweet potatoes than him?
I consider them to, well, first of all, I never remember what the difference is, and second of all, they're all done. Real honest potatoes, delicious. Sweet potatoes, yams, hell spawn. Just saying. Zero age main sequence. Next chapter, we're talking about star formation in the interstellar medium. Talking about when a protostar, when its core gets hot enough to initiate the proton-proton chain, a star is born and it becomes a main sequence star for the first time. It's a brand new spanking baby star. Don't spank your kids. But anyway, then we say it's on the zero age main sequence at that point. Zero age main sequence is when a star's just ignited hydrogen fusion in its core. When the sun was born, when it first started fusing hydrogen in its core, it was only about 60% of its current luminosity. And it has been slowly increasing in luminosity ever since then, as the core temperature increases. And what does this imply about the fraction of energy it's making from CNO versus proton-proton?
Making more from CNO.
Making more and more from CNO because of the fact that the CNO cycle is much more temperature dependent than the proton-proton chain is. So this says the ratio of the CNO generation, energy generation rate to the proton-proton energy generation rate has been increasing. And if I recall correctly, according to the models that James was making, eventually CNO will take over in the sun when it's old enough. So right now that's about 10%, but it's increasing with time. And so eventually CNO takes over. So there's no, in other words, there's no single mass above which you get CNO and below which you get proton-proton chain. It's actually a function of both the mass and the age of the star, whether CNO dominates or whether the proton-proton chain dominates. Now, if it's 5 solar masses, CNO, I don't even think about it. But if it's 1 solar mass or 1.1 solar mass, well then, well, tell me how old it becomes, right? Now, there must be some mass where it just starts out as CNO, is what it comes down to. But the sun is in the kind of range where, well, it depends on how old it is, which one is more important. But there's all kinds of interesting implications of this, because sometimes you will hear that, okay, well you know this, right? The sun is eventually going to turn into a star, not a red dwarf, a red giant star. When it's done fusing hydrogen, we're going to get to this, fusing hydrogen in its core, it'll switch to fusing hydrogen in the shell surrounding the core. It will swell up. First it will become a subgiant and then a giant. It will become about an astronomical unit across. It will eat Mercury, probably Venus as well. Earth probably won't get eaten, but on the other hand, it will become, at its peak, about 2,000 times or so more luminous than it is now, which will just completely fry Earth's surface. Not even the cockroaches would survive that, and sometimes that'll be depicted in popular media. Well, when the sun becomes a red giant, that'll be it for life on Earth. But actually, it's not going to take all that, as long as that. Life on Earth, unless our distant AI descendants do something about it, no, what do they care? Well, yeah, life on Earth, if it survives the AI apocalypse, will be extinguished long before the sun becomes a red giant, because the sun's getting brighter and brighter, and it's hard to say when because of the uncertainties of climate models and so forth, but it's estimated that between something like 500 million and 1 billion years from now, which is much less than the 5 billion years or so before the sun becomes a red giant, the sun's luminosity will be high enough that it will drive the greenhouse effect on Earth to become strong enough that it will basically, it'll start boiling the ocean. It'll start causing so much evaporation from the oceans. The water vapor, which is a very strong greenhouse gas in the atmosphere, will make a very strong greenhouse gas as a result of that, that will enhance the effect. And so the oceans basically, not literally boil away immediately, but they just kind of evaporate away, if you will. Ultraviolet light from the sun breaks apart water molecules high in the atmosphere, and then the hydrogen escapes into space. That water's gone for good. Meanwhile, the temperature gets high enough to bake carbon dioxide from volcanoes, which is now safely locked up as carbonate rocks in the crust. It'll bake it out of the crust. That CO2 will join the atmosphere, and we will have a very thick carbon dioxide atmosphere like Venus does. In other words, Earth will become another Venus. It will be more like Venus than it is like Earth now. And ain't nothing going to survive that, or at least maybe in the upper cloud layers with some bacteria or something like that. But the sun brightening on the main sequence will cause the demise of the biosphere long before the sun becomes a red giant, and that will be driven by this fact that the sun's luminosity is increasing as it burns its hydrogen. So one of the things that people who want to study possibilities for life in the universe have to consider is things like, well, how long does a planet stay habitable around a given star, given things like this? It's not just until the thing becomes a red giant, there's other factors in play as well. And this was free education. I hope you enjoyed it, because we're past time to go. You're welcome. I'm not going to charge you any extra from for it. I know. It's causing me to change all of my vacation plans. I need to take all my vacations before 200 million years from now. Otherwise, there won't be anything worth vacationing on. Yeah, and I hate it when that happens.